Next up, we have Vitushi Sharma from Goddard as well, and UMBC, who's going to be talking about LLMs. You've seen the timer.
Okay.
When it goes to red is questions.
Okay, sure.
After 12 minutes. Thank you.
Okay. Evening, everyone. I'm Vitushi Sharma. I'm postdoc in GCN team. So I will present our recent work on large language model-driven analysis of GCN circulars. Thanks, Judy, for the wonderful talk. So I don't have to go for the introduction of GCN. Here, I will convince how language models can be utilized to analyze the 30 years of astrophysical observational reports. So GCN, there are two data products with GCN. On the left, GCN notices is shown, which is by machine and read by machine. So it is structured data. On the right, GCN circulars are shown, which are written by human and are structured data. So it is free-form text and it contains rich information of scientific observations. So almost every observatory have reported their transient through the GCN circular, and it's a popular product. As we have known that machine is not only just right now in the condition of only analyze the data, but can also read the data. So we use the GCN circular archive for language model analysis. On the right, GitHub repository link is given for the code source. So why language models? On the right, GCN circulars evolution is shown, and you can see since the migration, since 2022, the number of GCN circulars have increased, and especially in the last year, it is almost double. So there is growing data for the GCN circulars. So now archive hosts more than 44,000 of circulars. So it is not possible to extract the information manually. And also it is human written and unstructured data. So it is difficult to be passed by traditional methods. Now the modern NLP is capable of finding the pattern in the archive and the information extraction. So with this purpose, we carried out two studies with these circulars. One is topic modeling. So we classified the GCN circulars using unsupervised and supervised techniques. And other is information extraction. So where we extracted the structured data, it can be anything magnitude filter. Here we used to extract gamma ray burst redshift from the circulars. So here, let me go over the topic modeling pipeline. So here the circulars are embedded in the space, and you can see that the blue one is unsupervised pipeline. So where like circulars are modeled in the embedding space, then their dimensional reduction and cluster methods were applied to find the astrophysical topics without any training to find a pattern in the archive. On the red, in the red color, supervised learning pipeline is shown. So there we provided the label data. So like suppose like based on observation bands, we provide a few percent of GCN circular, less than even 1%, and the messengers, different messenger circulars. And then we fine tune the model to find the and compare the similarity. So with this, we find the similar circulars together. So with the unsupervised pipeline, we find the pattern in the archive. Here we find different topics. So here, this is the embedding space where each cluster presents the different topics. So all the topics on the right side have like 4 important keywords are shown. So like for dark blue color, it is topic, all the clusters with GRB afterglow. And the red one is radio observation. And similarly, we find like Fermi GBM data together, BAT Swift data together. So here in this embedding space, each point represent the GCN circular text. So this is capable of finding the dominant topics. But for finding the accurately classified clusters, we go to the supervised classification. So here we decided 5 categories like high energy, optical, radio, gravitational wave, and neutrinos. And then we provided 40 circulars of each and trained them, fine-tuned the model using contrastive learning. Based on that, we compared the rest of the circulars with them, and we find the similar circulars are clustered together in this space. So blue one is optical observations together. Red one is the high energy observations together. Green one is radio observation. Yellow is gravitational wave, and purple is neutrino observation circulars together. So find the credibility how this pipeline is working. We find how the community has evolved in multi-messenger. So we can see clearly that optical, high, and radio observation has been there since the beginning. And we find the purple in with yellow color, the neutrino and gravitational wave community is there since almost last decade. So which is like quite similar to what we observe. And here, this is fantasy inspired land for observation type clusterings. So here is using the diffusion radar, this is created. So high energy observations like are red mountains. Blue one is optical observation sea. Green is radio observation forest. Yellow is gravitational wave ripple sand. And neutrino is shown as glacier field. So an interesting way of finding the clusters with our positional region. So now moving to the supervised cluster with more accurate to the users. So as GCN is being used by different users, some are observing interested in gravitational wave, some are interested in high energy neutrinos. So with this, we developed the customized pipeline as well. So code link is given here. Here, suppose user is interested only gravitational wave clusters. So with this purpose, we labeled the gravitational wave, non-gravitational wave, and gravitational wave labels for like 100 circulars of each. Then fine-tune the model, and again, with over the rest of the circulars, we place them over the embedded space. And there we find that blue one is non-GW events, green one is gravitational wave report, red is gravitational wave counterparts. As we know, like for 170817, which is famous binary neutron star merger, we extracted all the data and manually overplotted over this cluster in yellow points, and we find it is properly overlaps with the machine trained data. So out of this 277 circulars, only one circular was misclassified. So we find that it gives the promising results. Again, how the community, gravitational wave community has evolved over the time. So non-gravitational wave community has been there since 30 years. And the green and the red, which is gravitational wave and gravitational wave counterpart, peaks since 2015, when during O1, O2, O3, and O4 peaks are shown. So thus we find this classification pipeline works well for clustering the observations. Now gearing, change the gear a little bit. So this is completely different pipeline, information extraction, where we extracted the structured data from unstructured text. So for this, we use open source tool, Mistral. So we've provided the GCN circulars. Here the pipeline is shown in blue, which is RAG pipeline. So first is retrieval step, where we like used the neural search query keyword search, and we found all the relevant circulars which contains the redshift. Then these are processed to the prompt engineering. So the prompt template is created, and through machine, the JSON template, JSON output was extracted. So automated extracted information are redshift, event name, instrument, and redshift type. So here, unstructured text. Also here, this prompt template is shown. We can see this is for one example for GCN circular above, and the below is the prompt tuning template, and the JSON output from this template is shown here. So we can clearly see this for this GCN circular, the telescope is Keck Harris, and event is GRB 151027A, and machine is quite accurate in finding the values. Here, a side-by-side comparison table is shown. So we already have Swift Redshift table for comparison, and we created the what machine predicted versus what manually is written in the Swift table, and we can find that all the entities have similar value predicted versus actual GRB, predicted versus actual redshift, and so on. And we find that the achieved accuracy with this pipeline is almost 97% for extracting the redshift information from all the circulars. On the below, the redshift distribution is shown, which is obtained from all the GCN circulars and after post-processing. And details are given in the paper. So we demonstrate the potential use of LLM for transient alert system, and which is able to enhance the text mining, astrophysical text mining. And as there is a growing volume of data and heterogeneous and unstructured data, the machine learning infrastructure is capable of doing the unified analysis. Thank you all, and I will be happy to take the questions.
So we have time for a couple of questions for Vidushi. Yep. Gemma.
Yes.
Thank you for the talk. This is really impressive. I was wondering if these large language models could be used in order to generate a new notice topic type that could then be sent as a notice on the GCN. So for example, it's just being run on the archive and it's like, oh, I now know the GRB, whether it's short or long or redshift or something.
So yes, this is doable, and you can see with JSON, we can prompt tune and get the JSON output, whatever is required from the circular. The only thing is accuracy. So it depends how much community is fine with 97% accuracy or 90% accuracy. So that's the only thing. Yeah, but
I think that's pretty good. Cool, great.
Hi, Vidushi. Thanks for your talk. I'm interested in the failure modes of your supervised classifier. So do you know what are the topics of GCNs that get most misclassified with others and why?
So last sentence, sorry.
So in your supervised classification task, you must have a confusion matrix with some errors between some classes, right? I'm wondering which classes get most misclassified with others.
Okay. So as we increase the label data numbers, it went better. So in case of when it was unsupervised, the matrix was not performing well. It is in the paper also. And then for when we had 5 topics, the number of circulars were less. So it was 95% accurate. So there was similarity metrics. And then when you use the GW, where more 100 circulars were given, only in one case it failed. It recognized the GW counterpart in non-GW case. So it is actually accuracy. It doesn't fail, but it's accuracy drops or increase based on data.
So I'll ask a final question. So this reminds me a lot of work I did about a long time ago, actually, with a student where we were looking at astronomers' telegrams and the textual content of that. But one of the ideas we were thinking about was whether we could derive a concept scheme out of how astronomers were reporting what they were seeing to see if we could identify areas where there may be interesting missing things that we want to do. And I'm wondering, with the unsupervised clustering that you've been doing, do you see obvious areas where there should be something and you're not seeing something?
Good question. I have to think about it. So there are but because text similarities, it depends on language model. So yeah, how better the model, accurate is the result. There were the things where radio signal was taken from CubeSat data. If it is like classified with small models, it goes into radio observations. So there are things like depending on models that can be still corrected. And there can be a like based on like one type of circular, we can ask the machine provide the template of like how the optical observation looks like out of this training. That can be like something used for like if something is missing for like future coming ATELs.
It's interesting, yeah. There's potential there, I think. Okay, great. Thanks for
Welcome.
Dushika.